than 1.0 ohm. I intend to connect this cell with another cell in series and in parallel across a resistor. Then I'll vary the values of the resistance of the resistors connected across an ammeter in series. Then I'll connect a voltmeter in parallel with the resistor, then a switch to show what is going to happen. We're going to study what is going to happen when we do this connection. So this is a resistor. Now let me change the resistance of this resistor from 10 ohms to 2 ohms. So the resistance is 2 ohms. Then I'll add another 9 volt battery of internal resistance. Now I am connecting both batteries, both cells in series. So we'll have a combined 9 volts and 2 ohm internal resistance. So I'm going to connect this with a wire, connecting wire. Then I connect this to one end of the resistor. Then I'm going to connect a voltmeter to both ends of the resistor. Now you can see the voltmeter showing 0.0 volt, meaning that it is ready to take the voltage across the 2 ohm resistor once the circuit is complete. And I'll put a switch on this side. The resistance of this switch is infinite. Okay, let me bring an ammeter. So I can add an ammeter in series with the circuit. Then I'm going to connect all the circuits together. So I'll connect this. This is the connecting wire. Now in this experiment, you can see the flow of electrons. Now the ammeter is ready to take. Now let me close the circuit. On closing the circuit, you can see the current flowing through the ammeter to be 4.50 amp. Now this is because we have a 9 volt battery. We have a 9.0 volt two 9.0 volt batteries connected in series. The total the total EMF of the cells is going to be 9.0 plus 9.0. That will give us 18.0 volts, and the total resistance of the circuit is going to be 2.0 plus 1.0 plus 1.0. Remember, the 1.0 to 1.0 ohm resistance are for the two cells connected in series. So that's definitely going to give us 4 ohms. So when you divide 18 by 4 ohms, you get 4.50 amp. Remember from Ohm's law, I equals V over R. So the voltage drop across this resistor is 9 volts each times 2. So you have that 9.0 volt, 9.0 volt. When you add that together, you are going to get 18 volts. 18 volts altogether, and the combined resistance is going to be 2 plus 1.0. So that gives us 4.50 volts. Now you can see the direction of flow of current from the positive terminal of the cell or the negative terminal of the cell to the positive. That's flowing in the anti-clockwise direction. Now if I change the flow of, if I actually show the flow of conventional current, you're going to see it now. So you see the direction that it is flowing. It is flowing from the positive terminal to the negative terminal in clockwise direction. So the direction of flow of current is always opposite to the direction of flow of negative charge, that is electron in a circuit. Now the next thing I have to do, I want to increase the resistance of this resistor, and let's see what will happen to the current. So I've increased this to 4.5. Now you see that the current has drastically reduced to 2.75, and you see that the current slows down, the flow of current slows down. Let me increase this to 5. The current increased to 2.57, and you can see the arrows moving slowly. Now I have increased the resistance to 10 ohms, and the current flow in the circuit is now 1.50 amp. So with an increase in resistance, the current decreases. Now you see the total voltage is now 15.0 volts. The total volt across the 10 ohm resistor is 15.0. This is because you know that the cell has internal resistance, and from Ohm's law you have this equation. So we have I equals E over R plus R, where I is the current flowing through the circuit, E is the EMF of the circuit, R, capital letter R is the resistance across the resistor, small r is the internal resistance. So when you cross multiply, you're going to have I into R plus R equals a, open the bracket, you have E equals I times big R plus I times small r. So if you replace this with V, then you're going to have E equals to V plus small v, where V is the terminal PD. The terminal PD is the voltage drop across the resistor, while small v is the voltage lost, or the lost voltage due to the internal resistance R of the cell. Now following from that, you can see that the current flowing through the circuit is I equals 18 divided by 10 plus 2. Remember that the resistance was 10 ohm and the internal resistance was 1 plus 1, which was equal to 2. So you add that together, you get 18 divided by 12, which is 1.50 amp. And V equals IR, which was 1.50 times 10, which is equal to 15 volts. So that's the voltage drop across the resistance, the resistor, 15 volts. Remember that our voltage drop was 15 volts when we measured that. It was 15 volts when we used the voltmeter to measure it. Then the lost voltage, which is V equals to I times small r, is 1.5 times 2, which is equal to 3. But obviously you see that the voltage loss in the circuit is 3 volts, and that is the reason why the voltage across the external resistor is equal to 15 volts. Assuming there was no internal resistance, then the voltage drop across the resistance would have be 15 volts. I think we'll check that out again. Now back to our circuit again. Now you can see that the voltage drop across the voltmeter is 15.0 volts. See it around there, 15.0 volt. The current flow is 1.50, and the resistance of the resistor is 10 ohms. Then you see that the internal resistance of the cells or the battery is 1 plus 1, which is 2.0 ohms, and the voltage is combined together to give 9.0 volt. You see that from calculation, now you know the reason why the voltage here is never going to be equal to 18, which is 9 plus 9. 9 plus 9 is going to give us 18 volts. That's the voltage across. The reason why you cannot get 15.0 volt is because of the internal resistance across the voltage here. Now take a look at this. Let me remove the internal resistance of this circuit and see what will happen to the voltage across this voltmeter. Now take a look at the circuit. There's no internal resistance here. Can you see now that the voltage drop is 18.0 volt, which is the same as the sum of these two, and the current flow has also increased to 1.80. But because this time around we are going to use I is going to be the voltage drop, which is 18 divided by 10, which is the resistance of this, because there's no internal resistance. So when you divide this, 1.8 divided by 10 is definitely going to 18 divided by 10 is definitely going to give you 1.80 ampere. So you see the reason why there is no lost voltage here because there's no internal what resistance. Now what I intend to do is to connect these two batteries in parallel now and see the behavior of the circuit. Now let's see what will happen. Let me connect the circuit in parallel. The resistors, the cell has already been connected in parallel. Now let us connect other components and see how the circuit will behave. Now this is my connection. I have connected the voltmeter to the resistor in parallel. Then I have my ammeter to record current. The only difference from the other circuit is that I have connected the positive terminal of this to the positive terminal of this and the negative terminal of this to the negative terminal. In the previous connection, they were connected one end to another, and that is positive to what? Negative. Now let's take a look at and see what is going to happen. Let's close the circuit. So on closing the circuit, you find out that the voltage drop across the circuit now is 8.57, and the current flowing through the circuit is 0.86 amp. Now you can see that the voltage has reduced and the current reduced again. Now what happened here? Why is it like this? Now let me show you why it is like this, why the circuit is like this, why we have a reduced voltage and we also have a reduced voltage and also have reduced current. Why? Now in parallel, assuming there is no internal resistance, the voltage across this would have been the same as this 9 volt. You can see that they are very close to each other. Again, I'm going to use my formula again. This is my formula. I is equals to E all over R plus R. But take note of this, that the cells are arranged in series. So since the cells are arranged in series, I'm going to calculate the current, the internal resistance of the circuit. Now the internal resistance of this circuit is going to be this. Now look at this. The total internal resistance is going to be 1 over R equals 1 over R1 plus 1 over R2. So with that, now the internal resistance are actually 1 each. So I'll calculate that and impute these values for this formula over here. So we're going to have this. So I have 1 over R is equals to 1 over 1 plus 1 over 1. Obviously, this is going to give us 1 over R is equal to 1 divided by 1 is 1 plus 1 plus 1. Then let me just write this here. 1 over R equals 2. So you know what to do now to find the inverse of this. So just cross multiply. So I have 2R equals 1. Then R is going to be 1 divided by 2, which is 0.5 ohms. So that's the resistance. So the resistance is 0.5 ohms. So we know that the internal resistance is 0.5 ohms. Now we are going to impute that from our formula. Go back to that our formula now. We know that our formula is this: I equals E all over big R plus R. Now impute these values here. I'm going to have this. So I is going to be equal to E. The total, now because they are connected in parallel, the total EMF is just one of them. That's 9 divided by the combined resistance will now be 10 plus 0.5. Remember that our internal resistance was 0.5. Remember that it was 0.5. So 10 divided by 10.5 rather. 10 plus 0.5 is going to give us 10.5. On dividing that, we are going to have this. So on dividing, I'm going to get 0.85714, which is approximately 0.86. So the current is approximately equal to 0.86. Now you can see that is why we have this reading 0.86 amperes. So having gotten the current now you see the reason why we have this. Now we can be able to determine the value of this voltage here. So how do we get that? So remember this, E equals to V minus small v. That's big V is the terminal PD and small v is the plus voltage. The terminal PD is the voltage across this. So we want to see whether we're going to have 8.57. So from this you can see that V, let me just write here, V is equal to, our current calculator was 0.86 times R10. So when you multiply this, 0.86 is going to give us an approximate value of 8.6. Now bury our approximation, you can see that the value is close here. So though my value is to 1 decimal place, the value here is to 2 decimal place. Now you see the reason why the voltage drop is simply 8.6 volt. Now I want to show you something. When I remove the internal resistance of this battery here, let's see what will happen. Now take a look at the circuit. On removing the internal resistance of these two cells, you find out that the voltage drop across this resistor here is exactly the same as one of these, which is 9 volt, and the current that flows here increases, because this time around I is now going to be equal to 9, just 9 divided by what? 10, and that gives us 0.9. So you can see how circuit behaves when the cells are arranged in series and in parallel. In my next video, I am going to look at how circuits behave when resistors are connected in series and in parallel. Do not forget to subscribe. I will thank you for watching. Subscribe, like, and also share this video if you find it useful with your friends. See you some other time.